I'm so delighted and rather excited to have our next guest speaker, Professor of Astronomy, Professor Chris Lintott.
Welcome.
You.
Thanks. Thank you. This is going to be slightly different, I think, than some of the many other different things you've had this afternoon, for two reasons. One is I feel this is like the closing act of the festival. It's a bit more informal. Yeah. The tents have been taken down. It's probably beginning to rain. You know, we're just going to vamp for a bit, and then you'll tell all your friends you saw us. So that'll be good. The second reason, I think, is that I think I have a different relationship with music personally than lots of my colleagues. Both my parents are profoundly deaf. So I grew up, and this is true, in a house where the only music was musical theatre and Cliff Richard. And you can insert your own joke there, I think. And it took me time as an adult to find music, and it's become a hugely important part of my life. It's the thing I most enjoy doing, is being around live performance, and hearing Milt's lectures are part of that. But I don't have a theoretical understanding. I am musically not tone deaf, but I have a very poor musical memory, and so I sort of exist in this bubble in which music exists for me and is hugely appreciated, but I feel I have almost no understanding of it. And so this connection between us is about, I think, connecting the subjects in a sort of emotional way, rather than with Sarah or some of the others where you had a slightly more technical understanding that added to your understanding music. This is about the experience of hearing, right? And about listening to music, which underpins all of this.
Exactly. And, the idea of the music of the spheres is an ancient one. And remixing the music of the spheres is an idea of doing just that, using our modern knowledge, but the same spirit from those days. And when we think about music and astronomy, we can think of it a number of ways, like what music exists in space. So the first place would be to think of the Voyager. 77?
77, the first one's launched, and headed out via the giant planets, now still active in the outer solar system.
With messages of goodwill to our alien cousins, and some carefully selected music. Here.
Yes, which caused a huge argument. So there are these records, these LPs online, and the story's well known that these are physical records with instructions for aliens as to how to play them at 33 and a third.
Yeah, it's got very brilliant coding about what time is. It's down to the atomic level.
That's right. And various people were asked what to put on, and my favourite response is still somebody who said that the obvious answer was just to put Bach. But if we sent Bach into the universe, that would be boasting. So we should do so we have Chuck Berry and a whole host of other things on there instead.
So another way to send, this is not very efficient. It's very beautiful, and they've got quite far, but it's nowhere in terms of
That's right. These things don't
distance.
go near another star for the next few million years, and the odds are they will never be found. They're so small and so dark that unless aliens already know they're there and are planning to pick them up the moment they stop transmitting to us in about 10 years, this is an art project.
There could be some sort of garbage collection unit.
Yes, that's right. Yeah, the humans are doing it again. We'll go and tidy up.
Better still is radio frequencies, because we can send them out at the speed of light, which is astonishing. In fact, this is a project that I was involved with, which was shooting sound at the moon, and in 3 seconds it would come back. About 3 seconds?
A little less than that, actually. Okay. It depends a little bit on where you are in the orbit.
Okay.
What did you send?
This.
My name is Chloe, and I'm 6.5.
My name is Chloe, and I'm 6.5.
There you go. So my daughter's voice has been to the moon and back, which is rather beautiful.
There's actually a serious point here. So we often do this sort of thing because we think about how we detect signals from elsewhere, if people are sending us sound or radio. And so by bouncing it off the moon, you get a degraded signal, and you can test what you can make out of these signals. So, for example, people have done this by looking in light at Earthshine. When you have the crescent moon, you see the dark side shining. That's light from the Earth that's reflected off the moon and come back. And by studying that, we've discovered there is life on Earth, but we're not sure whether it's intelligent or not. But with the radio signal, that it's a sign of intelligence. So people have looked for music or signals from the stars, with no luck.
The fidelity is not great, and that's the moon, which is our neighborhood. But we can ask ourselves, how far has sound reached? We can think of us as, once we started producing radio waves, we've got this bubble, basically, and it's a historical bubble. So if we take let's say, the Voyager here, which is 1 light day away, but it hasn't got anywhere. But 1.5 light years ago,
And so on the other side, there was a...
what would we find about 1 light year away?
So that's last year. So this is last year's.
No, but what would
what's
you-
that? So you're still closer than the nearest star at this point.
Okay. So how about 45 light years away?
Yeah. So these are places where we know there are planets. This is Galactic 615. So they're watching our television from the early 80s.
70 light years ago, they would get this. I looked this up, is that correct?
Yeah, that's about
Such
right.
cool
Yeah,
names.
So this bubble, we're slowly populating with planets. So these are now places where we know there are planets. So there could be species listening to us and watching our TV.
And the furthest would be our first radio signals, which is the first I managed to get, 1922.
That's right. Yeah. So that was the first powerful broadcast. So this, just to give you a scale, so this is a 100 light year bubble, but our galaxy is a few tens of thousands of light years across. So there's this tiny bubble in the galaxy where they can listen in. There you go. Yeah, you've got it there. So you can imagine one way of thinking about this is a galaxy full of these little bubbles of civilizations broadcasting out. And what you want, if you're interested in chatting with aliens, or at least watching their television, is you need those bubbles to overlap.
Yeah.
And that's an open question whether that
That's
happens.
great. It's a cultural gradient as well.
That's right. Yeah.
They
It
get-
means if they turn up, if they were there because they loved the young ones in the early 80s, if they have some super duper drive and turn up, they're going to be disappointed there aren't more episodes. So you get all sorts of potentials for miscommunication.
But sadly, this is but a whisper, isn't it, in our cosmos? Space is big.
Space is big, and space is weirdly noisy. So friends who look for these signals, this is radio waves, so I think you could debate whether this is listening or not, but it's radio waves in space. The problem is more that we're loud. So a mobile phone on the moon would be much louder than the most powerful natural signal from space. So optical astronomers, people who look in visible light, we go to dark places. For radio astronomers, people who listen to the cosmos, it's a cacophony surrounding them, and it's about finding the one note in this background.
I mean, with the inverse square law, it just must be almost indecipherable.
Yeah,
from
but we
noise.
have powerful telescopes, so we're close to being able to detect
Would
airport
there
radar.
be a cleverer way to encode radio frequencies so that they would be lossless?
Well, this is where music comes in, I think. I think lossless is hard, but I think what you want to do is create something that's obviously
Logical,
different.
yeah.
And so that means pattern, that means rhythm, that means all of these things that you've been discussing all day. So I think transmitting...
low entropy things, because it's
yeah.
unlikely to be noise,
So,
by definition.
clapping patterns or something. I think if you wanted to be recognized by the cosmos, you'd send music. You wouldn't send a signal.
Another way of thinking about sound in space is basically what sounds like in these different areas. So this is Earth, which you might have heard of, and this is what sound sounds like on Earth.
This may sound familiar.
But not all planets are equal.
Yeah, well, let me introduce Titan before you do that. So Titan is a moon of Saturn. It's the only moon in the solar system that has an atmosphere. And it's a nitrogen-based atmosphere like ours, but instead of water, it has methane and hydrocarbons.
Very beautiful.
It's beautiful. Yeah, this is an infrared image. It rains methane in lawn tennis-sized raindrops that fall at about this speed on Titan, so you'd be able to dodge them. So it's a different atmosphere, and a very different, and it's cold. That's the other crucial thing. Cold and smelly. Yeah, but other than that, beautiful.
And what's interesting about sound on Titan, it's similar, but it's actually brighter. There's more emphasis on the top end.
I think that's the temperature is important there.
Okay.
So the physics of this is the temperature. But can you play both again? Because even I can hear a difference there.
Okay, so Earth, Titan. A little bit more top end, perhaps.
Sounds better, no?
Yeah.
I think. Right, concept
Titan mix, yeah.
Yeah, so we're not there yet, but we were talking about this, and I was telling Milt about friends of mine who are building a spacecraft called Dragonfly. And you can see a model of it in the Science Museum at the minute in their exhibition. But Dragonfly is going to be a little helicopter that bounces around on Titan. And so I think this combination, you've managed to put something together for.
Oh, yes. So actually, with Titan, we have actual sound from. That's
Yes,
most
that's true
amazing.
too. Yeah, we've landed one space probe which had a microphone on
Here's
it.
an animation of it, which is pretty awesome.
Yeah,
and
so this is the new one. This is Dragonfly.
And this is the actual sound recorded from it.
So this is sound from a previous mission called Huygens, which was a European mission that touched down.
That's too cool, I think.
Sound from another place is really interesting. And there it is, touching down. The microphone has a purpose, and this is from the surface, I think. So the microphone has a purpose because it tells you about the atmospheric conditions. If you have a camera, that's too good. If you have a camera, then you learn about where you are. If you have a microphone, and it's sensitive enough, you could pick up about what's happening in the distance as well. You can hear, for example, if there are thunderstorms, or what the wind's doing over the next hill. So
we always think of sight as the primary understanding, but sounds you can see in all directions and through objects and so on.
And at different sensitivities, and the dynamic range is higher. So sound has a purpose. So this is a real research project to find a microphone that can go on this mission.
And these sonic environments vary rapidly. Venus they must like dubstep on Venus. Super low.
Thick atmosphere, acidic, very hot would not be a recommended place.
And what we have is these different sonic signatures for different places here. It's like an EQ curve. This is the reverse because it's like what's attenuated, right? So if we listen to a bit of Holst's Venus on Venus, and then I'll put in the turn this up a little. There you go. I quite like it. The violin becomes distant and heartfelt. It's quite sweet, right? We should listen more on different planets.
Well, just before you do that, it's interesting because this illustrates something that Holst was doing that I can tell you about, because I think that's kind of a nice, it suits a summer's evening, that music, even on Venus. That feels very lovely. And that's, of course, because Holst was writing an astrological suite. Right, yep. So this is Venus, the bringer of love, a pleasant presence in the evening and morning sky, whereas we now know Venus is a hellhole with the hottest temperatures in the solar system, pressure that would crush you, acid that would dissolve you. So we need a new suite.
Switch the names. Well, what I liked is that they hadn't discovered Pluto yet. So they did that for ages.
Well, the number of people that have been commissioned to write Pluto as part of the Planetary.
And now they say, oh, never mind.
No one's done the others. Anyway, keep going.
Okay, So sound on Mars is super interesting because not only do you get an EQ curve, by the way, that's the saddest thing.
Oh, yes, this is the last message sent by one of the rovers.
It's heartbreaking.
But these are real pictures. So this is not CGI. These are pictures that have come back from, I think this is Perseverance, maybe? It's one of the recent robot geologists that we've sent.
And what's amazing about sound is that not only are frequencies attenuated differently, but they're delayed. So different frequencies happen later than others. So I've recreated the effect of it, and it's
So before you do, just say that happens on Earth as well, but the range in which that change happens, the physics where the frequency changes, the speed of sound changes rapidly with frequency, is way outside our hearing range on Earth. But on Mars, because of the different atmosphere, it's much thinner, it's carbon monoxide rather than nitrogen-based. It happens to be right in the middle of our auditory range. So if you're in the Martian air, having been genetically modified to breathe it, you're going to hear some
So is
sounds.
it just more subtle here, or are we accustomed to
No,
this?
at the range we can hear on Earth, the change is very, very small.
Right.
And in the ultrasound, there's a place where it changes rapidly.
Okay,
in
but Mars
that's
has
shifted
it.
down. Yeah.
So this tool here it's not attenuating signals, but it's delaying them. So here's a Holst's Mars.
Great.
And now I'm going to delay the lower frequencies. And what you get, these laser shoots. So you get these pshooms. Let me play you a little bit of that. So you get this moment here, which, let's see if it's correct. It's so nice, right? And so I was thinking about this, is that if we wanted to colonize Mars and we wanted to hear music on then you need to do the opposite, right?
Yes, the musicians would have to adjust, right?
Yeah,
knowing
so
how
you'd
far
have to
away.
do this, you'd have to do that, and then it would come out normal. and then it would come out normal. But the cool thing about all of this is that suddenly you have this amazing compositional ideas, and the idea, can we have a piece of music where the components come later based on their pitch? So every interaction, the conversation with these disciplines gets these musical ideas, which is why I'm here. I'm in it for me.
But I said to you when we were discussing this, my question was, right, we have to deal with why space sounds like Strauss, is how I would put this, if you remember 2001. But also there's all sort of library of sci-fi sounds, right,
so
that are acceptable.
there's a number of ways that we can depict space, and here's some here. So one of them, which is quite obvious, is to use unearthly instrumentations, things that you don't touch, that is ungridded in pitch and time, because it doesn't have our earthly trappings. This is Theremin playing his namesake, alongside the first electronic score, which is look at these cool dudes, Louis and Bebe Baron's score for Forbidden Planet.
So they're not following the scales that we're used to at all,
No,
or any concept of a scale?
Yeah, it's... so you get this...
There we go. See, it sounds like space, right? We've all been conditioned. That's not... Normally if an alien's around the corner, that sound.
And another thing we can do is basically superimpose styles. So everyone's going to be playing jazz in space. But if you put steel drum and a little synth, tiny bit, suddenly it feels alien. It's just a jazz tune. You hear that steel drum? That doesn't belong in jazz. That's all it takes.
That
for
feels
us.
much less alien than it did when this film came out.
Oh,
I think.
right.
Don't you think? Because the
Yeah,
genres
definitely.
have mixed a bit. Yeah.
So here's the fun thing. Another way to think about space is that in space we are reduced to the atomic level, like the elements themselves. And one to think about this is what is the most naturally occurring music, as opposed to cultural music, what comes from sort of the breadth of sound itself. And one thing is the harmonic series, just these emergent tones from it. So for example, here's the first 16. These would be the same across the whole universe. Scales wouldn't be, but these would be. And
maybe this is what we should be sending out if we want to emphasize that we're intelligent. This is
it was that, is it Contact where they send an intelligence signal, or in Close Encounters when they have
I think
music?
it's Close Encounters where it's music, yeah.
But one way to emit something primal is to use these as a form of musical structure. Super low C. There you go. How else might we do it? Well, Ligeti's Lux Eterna is an astonishing piece because it sounds ancient and logical because it's based on one melody, singing eternal light. But what happens is it phases against itself. So the chromatic structures start to compound, essentially. So you get alien structures, but a logic behind it. Right. So that's one way of making, implying.
So just to unpick that bit, it's sort of this sense that this logic that's alien. It's not just, that's what makes it otherworldly. It's not just like nothing you've ever heard. I think it's that uncanny implication that there's a logic
so what
there.
you have there is this juxtaposition of Latin text, which is ancient, and we have a human voice singing, but it seems sort of disembodied. Oh, let me find some. So it might have a melody like this, which seems familiar, but as they start to unwrap, you get these structures which are alien, but the core message feels familiar, which is
all of this, by the way, I always think when we're talking about space tourism a lot now, with people going to the space station, or perhaps maybe one day we'll all pay for a trip to the moon or whatever it is, but all of this is going to make very bad holiday soundtrack. I think. I just can't imagine being on a starship with a cocktail, listening to Ligeti, feeling kind of relaxed, and we're going to need some big bands or something. But sorry, yes.
No, it's fine. I'm having the best time. And what we decided is that, because it's the last lecture, we're just going to keep going till 6 and just have a nice time. Is that all right with everyone? So, we can say everything we want to say. So, for example, there's this idea that certain scales feel grounded. And as we discussed earlier, there's something about the circle fifths. Constructing scales in this way in the circle of fifths feels like we're on Earth. That's it. Feels grounded and familiar, but there is this one scale which extends the fifths one note further and loses that B flat, which earths us. And we get this scale, which has this floatiness, which you might recognize this from Wall-E. This lift that happens. There's this other moment which is really beautiful in Space Oddity, where when he's on Earth, it fluctuates between these two chords, C and E minor.
Ground control to Major Tom.
So this is E minor
Ground control
to E minor.
Major Tom.
It's sort of beautiful, but it's sort of earthly. Then when he lifts up, you hear this. He gets this chromatic lift as he launches into space.
Ground control to Major Tom.
Right there.
Really made the grade.
So musicians know how to make you feel weightless, basically.
Yeah.
And so go ahead.
Well, I was just going to say, before we leave Major Tom, there was the famous version of that recorded by the Canadian astronaut Chris Hadfield on the space station,
I know.
which people have seen on
It's quite
YouTube.
moving, I find.
Yeah,
yes.
yeah, and it's sort of astonishing. And it was important. It was so important to him to make music there that he found a way to get a guitar up there. He used all of his personal allowance to get a guitar onto the space station. It's still there. He left it for other people.
That's
there's
so
an
cool.
amazing song he did, which is the first Space Christmas Carol, which is also rather lovely. But I talked to him about recording Major Tom, and he said it sounded appalling because you're in a metal box filled with clutter. It's about the opposite of a recording studio. And so he actually said he found it musically relatively difficult to be there because all the sounds were, if you put headphones in, it's a very alienating environment. So even when you take the music up to space, you end up in these very different listening environments.
Not ideal. There's another approach as well, which is to create something like a portal. What I mean by that is that musicians imagine, sort of map harmony onto the sense of distance in space. So on the Imperial Death, what's it called, the Imperial March? It's in G minor, and he does this chord that he hits. He could have done any chord and got away with it and still got his money. He could have done this, which would have been totally fine, and no one would think less of him. But he chooses this chord. This chord. It's near but far. One note stays the same. The two move in equal and opposite directions, but we end in this other place. And there's this uncanny feeling as if Darth Vader's so evil he sort of breaks the fabric of.
We'll come back to the near but far idea in a bit as well.
It's that sound. This note stays the same. And you see John Williams intuitively does this thing of joining worlds together. He'll put A minor, that sort of sound, let me do it here, and then C sharp minor. That's the Death Star chord, if you're ever interested. Here it is. Beautiful. Oh, it's so gorgeous. But this all comes from Holst, where he plays this one melody in Mars. He goes G, D, and then he plays that note here. Before Led Zeppelin, by the way. And in fact, if you see this in the circle of fifths, G, D are right next to each other, and then we just portal over in this direction here. So you get And Euler did about everything. He actually mapped out this harmonic space, the idea that there's close chords and far chords, that these sound familiar if we go close and in this sort of direction, and these sound more distant. So what you'll find in space music is quick jumps very far away. The furthest you can go is a tritone away, and we hear this all the time. So we have this thing, and that's portal music here.
So this is writing for space, but astronomers, my predecessors for centuries, have talked about the music of space.
Yes.
About how, phrases that we're familiar with, like cosmic harmony, is a natural way of thinking about it, and particularly where people think about the clockwork of the solar system. It seemed natural to interpret this as music. This was sometimes from a philosophical or a religious bent, that the heavens should be musical to reflect better the glory of whichever god that you're thinking of. But also there's a sort of mathematician's logic to this. Music, as we've heard today, is in some sense a mathematical system that creates beauty and great complexity. And when we look at the universe as physicists, we want to find the mathematical system that can create this beauty and great complexity. And so it seemed to make sense to tie those things together.
And some of these are philosophical. I don't think the ancient Greeks were counting rotations of planets. You can correct me if not. But they had this idea that the planets were playing a monochord, were playing these harmonic ratios and making beautiful music.
Yeah, so we should say, when we're talking ancient Greeks, of course, we're talking about the naked eye planets, Mercury, Venus, Mars, Jupiter, Saturn, but we're also talking about the sun and the moon being planets in this sense as well. These are the things in the sky that move. And so they had a range of objects to think about, and they're thinking about the Earth being static and these things in orbit around us. And the great problem is that you end up with a complexity of melody. So the Greek writings about this, you want maybe to identify each planet with a platonic shape, or to say that there's a tone associated with each of them, but then you discover that if you use a regular mathematical sequence, then things get out of joint in the sky. And so they end up putting what are called epicycles.
Which are hacks, basically.
That's right, where you have a planet in a circular orbit, and then the center of that circle orbits the Earth, and then that doesn't quite work.
Because they didn't know the beauty of it. The system, they invented a complex one.
But this is the thing, the complex system worked. They were trying to build a system that could predict positions on the sky. And even right up to the 16th century, if you wanted to know where Mars was going to be, you could pick up the Greek tables and use the epicycles much better than you could. I can see Melissa nodding at the back. Much better than you could this modern sun heliocentric thing, because we didn't have the data. But this increasing complexity was justified in musical terms as well, because obviously with music you have a fundamental system of notes and then you build. So epicycles made sense, right?
Makes a lot of sense. What's remarkable is Kepler's descriptions of the, this is the eccentricity, it's the sort of shape of the planets.
It's affected by that. So this is the 17th century. So this is a period where you're sort of pre-telescope still, just about, and they had very good measurements of where the planets were in the sky. And what they're measuring here is how fast the planets are moving on the sky from night to night. How much does the position of Venus change compared to the background stars? Now that's affected by the size of the orbit, the relative position to Earth, and the eccentricity, as you see. But that's what they're visualizing here.
And what I didn't understand was just how accurate, how painstaking their measurements were at this time. And in fact, what's fun is that I could take his scales here and compare them with our modern tables.
Yeah, just before you do that, I want to point out this is actually an extract from that 17th century book, because with Milton, everything on the slide is usually his marvelous visualization. So this is Kepler, an astronomer, being a 17th century Milton, visualizing something for you, which is nice. So you can see the different planets have these different patterns. So Mercury, which is the one in the middle there, changes rapidly. And that's true. When you see Mercury on the sky, it tends to be moving from night to night rather fast. Venus
Is that sort of
changes very little.
flinging around in
It's
more of
flinging
like
around
a
the sun, and it's also very affected by, it's close enough to be affected by where the Earth is as well. So
right,
it changes
so
a
it
lot
whips
depending
over.
on whether we're seeing it on the far side of the sun or the near side. Venus, we see generally only when it's at the extremes of its orbit, when it's moving more slowly when projected onto us. So it appears to have a constant speed.
So Kepler was using a scale to denote speed,
Yes.
or was I think it was speed.
Angular speed is what
Angular
we're talking about,
speed.
yeah.
And I'm not sure what the base frequency was. I haven't been able to work it out. Well, maybe we can. I kind of tried to intuit it, but I couldn't work it out. But what we can do is recreate these and then compare them to what the max mean velocity and the distance would be. So this is Kepler's Saturn. And this is what it actually would sound like. Not bad, right?
No, pretty good.
It would be microtonal. And, he was dealing with steps, so he couldn't be more finessed. You can see with Venus that it's just all level.
Yeah.
So if let's take another one. We'll take Venus. So he would just have this. Sorry about that. But it actually sounds like this, if you can hear this, musicians. Just a little bend there.
So this shows how good their data was. This was from naked eye observation with giant instruments, many of which you've sat in, which is quite fun, done by people like Tycho Brahe, the great Danish astronomer. Lots of stories about Brahe I'll tell you about some other time. Incredible precision that enabled them to try and place this order in the cosmos.
But what's incredible is we can have as much fun now doing the same. So we have more accurate data on the cosmos, but we can recreate them. So for example, there is a scale that emerges from the solar system, judged on their speeds. What's fun is you'll notice there's C sharps and C, we'll talk about this later. There are 2 C sharps, there are 2 Ds, there are 2 G sharps. So it's kind of tuned. On the guitar, it could be a string per planet, but they're not in the right order. But this is the sound. It's quite nice, isn't it? That's our solar system.
Nice. So there's some order there. So people debated for about 300 or 400 years whether that was meaningful, that these ratios, are they random? We only had until recently one solar system to look at. And so people said, look, this sounds nice. There's some harmonic order here. Is that random or is that the consequence of what's going on?
Everything's fine. But actually, if we do it microtonally, then it's a bit more of an acquired taste. And then the asteroid belt, and then we get the gas giants. So together you get this sway.
And what you can hear is that as they discovered Uranus and Neptune, confidence in this cosmic harmony dropped, right?
Exactly.
Because they didn't quite seem to be fitting, and so...
Yeah, I want to talk about, is there any advantage for a planetary system to be harmonic?
Right, well, the great thing we can do now is this is one solar system, but we now know of about 4,000 other solar systems.
Yes.
So many of which have multiple planets. So we can play this game.
I'll just play a little bit. This is our solar system in rhythm and pitch, and we will just let a few enter here. So we have Venus, we'll have Earth.
And the pitch is to do with the size of the orbit here.
So
right?
it's the orbital period,
Yeah.
how often it is, but also the rhythm gives you it at a lower rate. So you're getting rhythm and pitch at the same.
Okay.
And this is microtonal, but it's quite pleasant, right?
Yeah. It's going to go wrong when they're large. So there's this gap. So this sort of harmonic argument was used to argue there should have been a planet somewhere around here. And when they found the first asteroids, they thought they'd found that planet.
It should have been a note, because there's a big gap.
Exactly.
We might have some big bass coming in here. You might feel it in your stomach at this point here. Let's move on, shall we?
Let's get Jupiter around once.
Okay.
There we go. All right, I'm happy now.
Okay, good. This is online.
So we can play this sort of game for different systems. So, for example, we've got here a sonification. Is this a Matt Russo one?
Yeah.
Yes, this is from my friend Matt Russo. So this is a system, I'm just going to talk about it for a sec. So this is a system called TRAPPIST-1, which is a relatively nearby system. It's 40 light years away, so they're watching what? TV? They're in the, 85? So if you think about TV or music from them, that's what they're enjoying right now. It's called TRAPPIST because it was discovered by a bunch of Belgians, so it is named after the beer. And it's a system with 7 planets we now know of. but it's like a concentrated version of our solar system. So the furthest planet, and they're clustered around a small red giant star, a much fainter star than the sun. The furthest out goes round in just 19 days. And so we can play this sort of game again and see if there's any harmony there.
Again, this is faithfully produced. You'll hear the microtonal friction.
So that's TRAPPIST 1A, sorry, B, yeah.
That's me tuning up the guitar. So much for the harmony of the spheres.
Yeah.
Right?
I don't know, it doesn't
No,
sound
I
too
love
bad.
it.
But you can see there's not quite a relationship there. They're
Is
all
it
playing-
becoming more harmonic over time?
So that's an interesting question. We think there's a big argument about whether these systems are stable and whether our
Why
solar
is
system
it
stable.
useful to be harmonic?
Well, we'll get to that when we show the next
Okay.
example. So just one last thing to say on TRAPPIST-1, which is that all of these planets are so close that they're probably tidally locked. So just like the moon keeps its face to the Earth as it rotates, most of these planets have their faces locked to the star, so they'll have a hot side and a dark side. So Floyd would be happy here, Milt.
Yeah, for sure.
So we've played with this for all sorts of things, but I want to talk about a system we found.
Next.
So this is a K2138 system. So if you go on to that side, so this is a visualization. So when we
Who names these?
So they're sort of catalog
can I have a
numbers.
word
It's a
with them?
bit controversial. K2 is a mission. So it was the
Okay.
second Kepler mission, and this was the 138th system.
Do they sometimes get nice names as well? Like
There's an attempt to give them nice names, but no one uses them. People use the catalog numbers,
Okay.
which is rather
But
sad.
it should be like animals, though. You know, you get the genes.
I think we should, we're about to discover, next year we'll discover about 5,000 new planets, so I think we should auction them off.
Yeah.
You can all have one, just take your pick now. But K2138 would be mine. So this is a 5-star system. They're called 5-planet system, B, C, D, E, and F. And again, it's a compact system. So Mercury would be about here if this was our solar system. So it's another crammed in system. But if we play Matt's sonification of this one,
Pretty.
it's much nicer. And these planets are in resonance. So each one roughly takes for every 2 orbits the innermost one goes round, the next one takes three times as much, and 2 to 3, 2 to 3, 2 to 3.
What's amazing is that I had this project called Distant Harmony where we just source all these planets because you've got endless chords, right? And reasons to have
Yeah.
them. It's not arbitrary. But I find it interesting that the 3-to-2 ratio,
Yes.
which is the fifth that we've heard about all day long.
That's right.
That seems to be this common thread.
Yeah, and we know quite a few systems like this now. So what we think it shows is that these things have evolved together, that they formed in a disk, they moved through their solar system while feeling each other's gravity. So it's a dynamical system that's locked by gravity.
So let's say there's a sun here, a star here.
Yeah.
If they all moved, they wouldn't ever move together because
No, they wouldn't all line up, but it means that, for example, when planets form, we think they migrate through the disk. So they move inwards or outwards. So these will have moved inwards or outwards together. So they must have formed
Is it
at the
that
same time.
inharmonic ones hit each other, or they?
We think what happens is when they hit this harmonic, then their gravity lines up because they line up every few orbits, and at that point, the rest of the material gets thrown out of the system. So you get locked, and suddenly you run out of other materials. So you stop migrating, and you freeze into this nice harmonic system. So this may be the end point. If you have enough material, all star systems.
It'll stabilize.
Yeah, and we will have run out.
Why is that
took-
so beautiful?
It's cool, isn't it?
It's amazing.
But we can also use this. If you go to the next slide, we found a 6th planet in this system about a year later, G. And then this graph just shows you, so the top is the period for each one, so G goes round in about 40 days. And then the bottom graph is just the difference. So you can see G is nearly but not quite in the same sequence. It arrives on each orbit about a day and a half late compared to what we'd expect from this 3-to-2, 3-to-2, 3-to-2 pattern. This is really annoying. Because if it was completely different, it formed later, it formed somewhere else, it formed in a different way or at a different time, no problem. If it fitted the pattern, we've got a pattern that we understand. The fact this is slightly wrong to a
does that
physicist
mean?
is annoying. It's a bit like a note that's slightly wrong.
So
right?
is it that it hasn't settled yet?
That's possible.
Or can it just support wrong nodes?
There's no reason for it not to. It can have whatever orbital period it wants, I think. But why is it nearly there? And
it's still tuning up,
What we
right?
think has happened, just as if you have a note that feels slightly wrong, often it's the composer that's put it there, right?
Yeah.
You've made a deliberate choice to be there. You haven't just plonked the keyboard.
Yeah.
So we think there might be another couple of planets hidden in this gap between F and G, which we're not seeing, whose gravity is pulling G forward or back and making it appear late. So this is evidence that there are other planets there, which we're now looking for. Shall we finish on the biggest scale of all? Do you think? Or do you want to go
this
for
one
the
here.
deepest?
Let's go with
Do you want
this.
to go here?
Yeah.
Okay, so enough planets. Let's talk about the universe as a whole as a grand finale to your festival. So often when we talk about music and astronomy, we're accused of cheating, because we've told you about sound in space, talked about radio waves, which are not sound, and we've sonified things. But there's a time in the universe's history where sound really matters. For the first 380,000 years after the Big Bang, the matter in the universe was dense enough that sound waves could propagate through empty space. At the beginning of the universe, in space, they could hear you scream, genuinely. And we see light from this time surrounding us. We bathe in ancient light from this time 380,000 years after the beginning. And we can map it on the sky. So this is a map of that light on the whole sky, translated into density. So blue bits are slightly less dense, red bits are so other way around. Red bits are slightly less dense, blue bits are slightly denser.
Why not uniform?
Sorry?
Why not uniform?
Why not uniform? That's a good question. We think it's to do with the very Big Bang itself. So it's an imprint of whatever happened at the Big Bang.
Splintered, sort of.
Yeah, or it got frozen in at that point. But really, this is a sound spectrum. So we can play the entire universe as an instrument for you.
And this is it. And what's beautiful is that we can actually zone in.
On different bits of the
And we're
spectrum.
actually hearing moments.
Yeah, you're changing scale there. So you're looking at large scale or short scale. And I want to acknowledge that this sounds pretty terrible. Right? I mean, we gave it the big
I'm doing my
sell.
best here.
No, some people like it. We've got a fan of the universe at the back. This is good. But it's because these sound waves propagate on almost all scales, you're getting close to white noise. So it's not a tuned instrument.
Yep.
And over time, this note has changed in the universe. And
Settled
so what we see
into
now is
these
different.
low entropy objects and into these harmonic.
That's right. So this
ratios.
is genuinely sound in the early universe that we're playing you, that we see embedded in this cosmic microwave background, which is the oldest light in the universe.
That's a pretty metal way to end. Thank you, Chris Lintott.
Thank you.
You're absolutely wonderful.
Thank you.